In this video, I'm going to be telling you more about path integration. And really, this is going to be path integration with respect to X, or with respect to Y, or with respect to Z, which really isn't going to make a whole lot of sense. So I'm going to just be kind of like trying to convince you of some things on an algebraic level, and then I'll come back in the next video and we'll integrate vector fields over a curve, and you'll see that this is actually what we're going to end up doing. But I think that if I just started out trying to justify why I would want to integrate f dotted with dr in the first place, and then got to this, that might be a little much for us to bite off in one go. So I'm just going to start us off with an example right here. This is something that if you looked at, you'd be like, I don't know what this means, right? You'd be saying y squared dx plus 2xy dy within one integral over c. Like, what is this? And so what I want to do is I want to just kind of like unpackage what we're talking about here. First, I'm going to need to parameterize curve C, right? If we're given a picture of the curve, we need to come up with a parameterization for it. Oftentimes in the problems, I'll give you a parameterization for a curve if it's not like a circle or something pretty obvious. But in general, coming up with a parameterization for a given curve is really good practice, and it's something that we don't practice a whole lot in the classes that lead up to this one. So I think, got to get it in while we can. All right, so first things first, let's parameterize C. It's a circle centered at the origin, radius is 2, so I'm going to use 2 cosine t and 2 sine t. Okay, thanks. And I'll say that t is going to run from 0 to 2 pi. Okay, and while I'm at it, if I've got x and y, and I've got dx and dy over here, might as well go ahead and kind of just write down a formula for those. Okay, we know that dx dt would be negative 2 sine t. Okay, so dx would be negative 2 sine t dt. And in the same way, dy is going to be 2 cosine t dt. Okay, so what I'm proposing is if I actually just, hold on to my faith and just plug all this stuff in, I'm going to end up with a single integral, okay? We know that if we're going to integrate over a curve, what we need to do is we need to parameterize that curve and then turn it into a single integral over the bounds of the t bounds of that curve. So I'm interested in the integral from 0 to 2 pi of y squared. Okay, y squared is going to be 4 sine squared t. Dx is times negative 2 sine t dt. Okay, y squared dx plus 2xy. Okay, so that's 2 times 2 times 2. That's 8 cosine t sine t. Whoops. And dy is going to be 2 cosine t dt. Okay, so that's kind of a lot, but it is, if you look at it, going to be a single integral, right? I could factor out the dt from both of these terms, and I would have the integral from 0 to 2 pi of 4 negative 8 sine cubed plus 16 cosine squared 1 power of sine. dt. And as y'all know, this is the type of thing that I could put through a calculator, right? I don't have an antiderivative for sine cubed t off the top of my head. You could probably use some sort of power reduction formula, but you don't want to go there. And this cosine squared t sine t, I imagine there's some sort of antiderivative for that out there. I just don't know immediately, and this is not the focus of this course, is finding the antiderivative for this. So, up to your ability to find an antiderivative here or use technology, you're going to be able to compute this integral. Okay? Now, still, what does this actually mean? You don't know yet. Okay? But this is kind of like the mechanics we're going to go through to compute a line integral with respect to x and y in this case. I think I want to do another situation right here. It's actually a little simpler, so I can just show you a little something to be aware of. So yeah, let me clear that off real quick. All right, yeah, so I've got a line segment here that I want to integrate over. I'm going to integrate, kind of a relatively simpler integrand, and I'm going to integrate with just respect to one variable this time, rather than doing two together. Now, eventually you're going to see a lot with two together, or eventually three together maybe, and that's kind of where we're headed. But I just want to point something out about this kind of operation, as opposed to the other path integrals that we ran last time with respect to arc length, right? And that's going to be the effect of the orientation of your curve. So I've actually I'll just pick up my white piece of chalk, and I'm going to say, at first this is a line segment going from 0, 0 to 1, 2. I'm going to say, oh, that's like y equals 2x. So I'm going to use x equals t and y equals 2t as t runs from 0 to 1. This is not the most difficult parameterization ever, but right? X equals t, y equals 2t, t runs from 0 to 1. So that is going to necessarily imply this kind of orientation along the curve. Okay, what I'm going to do is I'm going to compute this, and then I'm going to go and do it, reverse the orientation and compute it the opposite way, and you'll see that probably it's going to come back the opposite of what we got the first time. So in some sense, the parameterization, the orientation does matter on these integrals with respect to x, y, z. Anyway, what was I going to say here? I've got my parameterization. I need to turn this into t's, right? I'm going to need a dx. Okay, so dx is going to equal dt. That's going to be convenient for me. Okay, so this is going to be equal to, let's go and let's run an integral from 0 to 1 of 3 times x times y. Well, that'll be 3 times t times 2t will be 6t squared. Maybe I'll even write it like that, just to be safe. And dx is going to be dt. Okay, I think we can do this. This is going to be 6t squared dt, which is going to be, hold on, I think I've done something wrong here. Anyway, that'll be 3t squared as t runs from 0 to 1, which is going to be 3. Yeah, hold on, this is not the answer I was expecting to get. All right, yeah, that was odd. The book I was working on had a typo, and I think that they really wanted to integrate this with respect to y, because that was what they did when they were working the solution. But in the statement of the problem, they said dx. So I'm going to just stick with dx, because it's just the same. Okay, so, yeah, again, if I get the integral of 6t squared dt, that's going to be 3t to the third as t runs from 0 to 1. That's going to give you 3, right? Okay, but what if I had parameterized this the opposite way? What would happen, right? Let's see. Well, what if we had parameterized with, what if this was t equals 0 and this was t equals 1? Let's just try to figure that out. Going backwards. All right, so if I'm going from 1, 2, which is t equals 0, to 0, 0, which is t equals 1, I'm going to need to say, well, x is going to start with 1 and then lose t over time. Well, if I lose 1 over 1 time in increment, that'll be 1 minus t. And y is going to start with 2, and it's going to get smaller. And by the time t is equal to 1, I need to have 0 y's. So I'm going to be subtracting 2t. And then t is still going to be running from 0 to 1. Now what's going to happen is I'm going to still be integrating from 0 to 1. Okay, it's going to be 3 times x times y. So 3 times 1 minus t times 2 minus 2t. You can see the algebra here is going to be much less pleasant than it was over there, somehow indicating the importance of choosing a good parameterization for our curve. But that's a different discussion. 3xy dx is going to be negative dt. Right? So what I'm going to do, I think I am interested in, okay, I know what's going to happen. This is going to give me 2t squared. I would prefer to have a 3t squared, right? So I'm going to leave this 3. But I might just go ahead and factor out the negative. All right, so when I go and distribute, I'll deal with the t squareds first. I'll have 2t squared multiplied by 3. That's going to be 6t squared. As t runs from 0 to 1. Okay, and just the regular t's, I'm going to have negative 2 of them. Minus 2 more is negative 4 times 3 is negative 12. And then in the constant, I'm going to have 2 times 3 is 6. Okay, this kind of annoying, but it's not the end of the world, right? It's going to be the negative of 2t to the 3 minus 6t to the 2 plus 6t as t runs from 0 to 1. Okay, well, when I plug in 1, I'm going to get 2 minus 6 plus 6 is going to be 2. What has happened here? Okay, this was definitely not supposed to happen. Hold on. I found it. Okay, this is the danger in me recording these videos without people in the seats in front of me to catch my errors. This is what I should not have been doing mentally, right? Should have found an antiderivative, increase power by 1, divide by the new power. That's 2t to the 3rd from 0 to 1, which is going to equal 2, which is not 3. So over here, when I go and I plug in 1, and I get negative 2, get the opposite of what I'd had before. Okay, one thing I went and consulted with the textbook, and of course, since they did a dy, that was very little help to me. But one thing I'll just point out to you, how they anti-differentiated this was, I found kind of interesting. They left this 3 here, factored out the 2 from here, so they had basically negative 2 times the interval from 0 to 1 of 3 times 1 minus t squared. It's like, oh, that would be a nice antiderivative. We could do that. I would not have thought to do that. I would have just thought to, distribute and just take it the whole way like a polynomial. But okay, so here we've got an illustration of how, with these, reversing the orientation of the curve makes the path integral the opposite of what it would have been with the opposite orientation. This did not happen with the ones we did last time, basically because arc length, in general, we were always, kind of going with respect to arc length, small piece of arc length. We always thought that was positive, and we were always going to add it up and, going in the increasing arc length direction, regardless of if we started, here and went there, or there and went here. We were always just going to kind of count the arc length going up. Whereas here, we've got x starting with something and then decreasing. And so that's really kind of the mechanics at play here. I think that's going to be all. Let's just look. Let's see. There was something I wanted to point out from page 1120. But all it says is page 1120. Yeah, I think that, let me look real quick. Oh, so, just one of the things I wanted to point out more generally is that if we're faced with one of these things, dx, dy, even dz, or whatever, and we need to run a path interval on it, what we're going to do is we're going to notice that, suppose we've got some curve C. C is going to be parametrized with an x of t and a y of t. And maybe this is in space and it's got a z of t as well. Okay. So, Now in the textbooks, what you might see is, you might see them call this, F, G, and H, or G and H and K or something, I find that to be a little too much to hold on to. So I'm just going to say, X of t, Y of t, Z of t, that parameterizes the curve. X, Y, and Z are oftentimes things we want to integrate, some kind of function over this curve for a variety of reasons. Okay? Some of which we've seen, some of which are left unseen, and you will discover on your own. But when we are faced with an integral that's dx, one thing that you might be interested in remembering is that, we can just use this idea that dx dt is x prime of t. So dx is x prime of t dt. And you can say the same for the other variables. dy is going to be y prime of t dt, and dz is going to be z prime of t dt, which is going to be something that you're going to kind of like make a little substitution on when you're confronted with the integral of, 2x cosine y dy along some curve. Okay? And then, at this point, we have the tools that we need to move forward and integrate a vector field over a path.